So let's get to the classical neural networks because I want to use this analogy. Okay, I think Sebastian used this as well, but I want to use this again. In classical machine learning, okay, who is familiar with neural networks, first of all? I am going to assume that you've heard of neural networks. So don't worry, I won't ask you to raise your hands. So in classical machine learning or classical neural networks, what you have is you have some input X. Thank you, Christopher. You have some input X, and you're training the weights, W's, right? And the arrows represent the weights. These nodes represent the value X. You apply this weight on X, you get something, you apply another set of weights again, so on and so forth, until you get some value F, right? And this is known as the cost function or the loss function. And what you do is you try to minimize this loss function, right? This is how all the neural networks work. This is how LLMs work. The large language models, AI, ChatGPT, all that. You're trying to minimize some objective cost function, okay? And the thing that you're training on are weights, W's. In this case, it's theta. So the thing that you're training is thetas. The input is X, and the output is this cost function. Now, the goal is to find a list of optimal thetas that will minimize this cost function. Similarly, in variational quantum algorithms, that includes VQEs, QAOAs, something called quantum neural networks, which I'll also get into. You start with some state, 0, 0. You prepare your state with UX. Okay, so this is just state preparation part. And this is preparing some state psi, let's say, right? And then on this, so this part, I haven't, so this is still my input, okay? So this is the state preparation before this arrow. And U of theta contains a set of trainable parameters, or the parameters that I want to optimize. So that's theta. Just like in classical machine learning, the weights were my trainable parameters. And then the outcomes of this quantum circuit, which will be measurement values, using that, I will compute the expectation value of some Pauli matrix. In the case I showed you, I did Z, okay, but you can do X, you can do Y. But let's say we're doing just Z measurement. And so I compute the expectation value, F, like that. So this part is only quantum, right? So once I get the bit strings, I will do post-processing to get this F by doing multiplication and subtractions as necessary. And once I get the F, what I'll do is I will hook it up to a classical optimizer, right? And I'll give this to the classical optimizer. And the classical optimizer will tell me what will be my next theta. How do I update this theta? And then once the classical optimizer tells me that, I'm not going to change my input, it's fixed. I'm going to change my theta. I run this circuit on a quantum computer again. Quantum computer is going to give me some output. I compute this, and then I give this to a classical optimizer again. And that's again going to tell me how to change this theta. So on and so forth. Keep on doing it until this f of theta is somewhat minimized. Okay, I say somewhat because I can also get stuck in local minimums. That's the problem. But let's say I'll get some minimum solution. So there will be some suboptimal solution, right? Yeah, so this is the idea of variational quantum algorithms. Okay, so this is summarized in this diagram. So in this diagram, so step 1 is prepare initial state psi, apply sequences of unitary gates you want to apply. It can be one unitary, it can be multiples. These thetas are the thetas you want to optimize. You calculate the cost function. You pass it to a classical optimizer that will tell you what new theta I need to, and then I update this and I keep on iterating until this is minimized. Now, this is all fine and good, but the reason why this makes sense is because of just the mathematical proof I gave you. Because the expectation value of some observable with some state psi has an upper bound to some value, right? And that value, we call it minimum energy. So it has a minimum energy, right? And we're gonna get there. Okay, great. Now, this is all I'm going to say about VQE. Can I get thumbs up if this is clear to you? Then I'll get into the theory of QLA. Okay, I see 2, see 3. What about the rest of the people? Okay, I see a few more. See one more. Okay, I'm going to assume that it is clear, but not again. You can ask questions. This is great. Let me make sure that I'm on time. Okay, sorry. Let me go back. Okay, so now let's get into combinatorial optimization because this is what most of the people are interested in, and a lot of the problems in real world out there can be phrased as combinatorial optimization. Okay, so combinatorial optimization usually involves a set of binary variables represented by bits, and there are a bunch of constraints, and you essentially want to do this constraint optimization, right? And this is a problem that is solved with a lot of classical algorithms with neural networks. So the goal in combinatorial optimization is essentially minimize this cost function, this objective function. Usually, this objective function can be written as a function of n length binary string, and it usually has two values, 1 or 0. So for example here, so this guy will just take 1 or 0, 1 or 0, 1 or 0, and there are a set of clauses or constraints, and in this case, for example, there are m clauses. I won't leave this as a okay, so I will get into an example, but before that, I'll tell you the goal. So the goal of this is to minimize or rather maximize. You can phrase it in either way. The goal is to minimize some function. So what I mean is that a maximization problem can be phrased as a minimization problem, right? How you do it is you just add a -1 in the beginning if it's a maximization problem, and it becomes a minimization problem, right? So you can switch. So the goal is to find the string z that basically achieves something called this approximation ratio, where with this the string that I found, the ratio of that with the actual maximum cost is bigger than or equals to some r. So usually this r is, let's say, 90%. So by 90%, I mean, because I'm trying to find some solution, an approximate solution. So if it was an exact solution, then this ratio would just be 1, right? But usually, you can aim for 80, 90%, and that's the goal of combinatorial optimization, okay? All right, so let's look at an example, maximum cut. Okay, so Sebastian used this. I'm going to use it again. And I'll also use it again in next week, optimization week, when we'll talk about different optimization problems and solutions to that. But this is a very simple algorithm to describe. If this was not clear to you yesterday, now is the time to ask questions. So suppose you have a graph. Okay, I use a square graph with 4 vertices and 4 edges. The goal of this is to find the maximum cut of this graph. What does that mean? So maximum cut is usually like tricky visually. So what I'll use I'll use the idea of coloring. So what I want to do is I want to color the vertices with red color such that the number of these yellow edges is maximum. And the yellow edge is defined whenever I have a pair of vertices with different colors. For example, 1 and 2 has different colors, so it's colored yellow. And this is a cut. This is the idea of max cut. So in max cut, this would be a cut. In this graph coloring problem, this is just a yellow edge. Okay. Note that I'm not coloring the vertices. Okay. The colors are, sorry. So in the beginning, I'm given blue colors, okay? And my goal is to add red color to the vertices such that the number of edges with differently colored vertices is maximum. And an example of this would be if I color this vertex as red, then this edge has two different colors, right? So blue and red, and I'm using the yellow color to denote that for visual purpose. I'm not coloring the edge. And again, this will also become a yellow edge because this has two differently colored vertices. However, this is still the black, right? Because these have blue vertices and this edge also has blue vertices, right? Both of them. So the goal is to color the vertices such that I find maximum cut or the maximum number of these yellow edges. Is that clear? Okay, I'm going to assume that it is. And if this is not, then you'll see in this example. Okay, so if I was trying to find all possible sets of colorings, there would be actually these many possibilities. Okay, so here in this case, it's 4 times 4 is 16, or rather 4 to the power of 4, 4 to the power of 4, 4 times 4. So if I was trying to solve this, let's say, with brute force, or let's say I want to go through each individual solution and then find the optimal solution, then in this case, you can see that there are 2 to the power of 4, right? Which is 16 possibilities. 2 because I have two colors, and then 4 is the number of vertices. If I have 10 vertices, I would have 2 to the power of 10 solutions. If I have 50 vertices, I have 2 to the power of 50. If I have 100, then I have 2 to the 100, and that's larger than like the number of atoms in the entire universe, right? So if you look at this slide, do you see the optimal solution? If so, can you please point it out for me? Anyone? Do you see the optimal solution here? Okay, so okay, Alex, Alex found it as well. See, 2, 3, and 3, 2 from Basha. Okay, Anthony said that as well. Okay, yeah, that's correct. So this one and then this one, yes, that's correct, right? So this has basically 2 global solutions, and because all the edges have been colored yellow because the vertices are of different colors. Okay, great. So we don't want to look at every individual solution because, as I said, the number of possibilities goes exponentially up. And this is where this algorithm QAOA comes in. Okay. And so, Alex, can you help me remove this? Thanks a lot for your...
Sorry, just trying to work out how to do it.
Okay, it's fine. I'm going to move to iPad anyways. So the idea of QAOA, which is proposed by by 2 people, it was Fari and I think Goldstone. So this serves as a variational algorithm tailored to find approximate solutions to combinatorial optimization problems. Why is this a variational algorithm? I'll talk about this. And this is designed to be executed on the near-term devices. And again, so the idea of running circuits on near-term devices is we'll run small depth circuits on these devices, and we'll use a classical optimizer to update the parameters. Okay. Because people are like, what are we going to do with, devices with few hundred qubits, right? And this is where, like, for example, Fari came up with this example of QAOA, which I'll get into. So the steps of QAOA are as follows. So define a cost Hamiltonian so that its highest energy corresponds to the desired solution. And define a mixer that does not commute with this cost Hamiltonian. Okay, this is written like this, for example. So in the case of max cut, right? So if it was a weighted max cut, it would have weight. In this case, this is just 1. So it does make sense because if Gi and Zj have eigenvalues +1, then, sorry, both have the same eigenvalues, then this term would be +1. If it is +1, this would be 0, okay? When acting on a state. If this is 0, that means that, okay, let me go back to my graph. So if these two vertices are differently colored, then I'll assign, so for example, red is +1, and then blue is -1. I'll use that, I'll use those two numbers to represent red or blue. And so if two vertices are of same color, multiplying them will give me 1. Okay. So and so this term will be 0 if the vertices are of same color. However, if they are of different color, then this will be -1, and then I'll have 1 minus -1, which will be 2. Note that this is identity and not 1, because I'm working with operators. But if you talk about the eigenvalues, identity has eigenvalue +1. And you can see why this is a valid representation of my problem. And this is the first step of variational quantum algorithms start, which is, given a classical problem, you want to phrase it as a quantum problem. And to do that, you need to use operators. And then using operators, we'll get into the circuits. Okay, so this is the skill that I want you to cultivate if you want to use variational quantum algorithms. The reason why this mixer is used, which is the sum of the Pauli X gates, was described briefly yesterday, but I can do it myself. But does this make sense why this is a correct Hamiltonian? This is because Pauli Z operator has two eigenvalues, +1 and -1. That's why. Okay. Yeah. And so the third step is really just exponentiating these Hamiltonians with some parameter gamma and beta, just like Sebastian did in his yesterday's lecture. And then now this will become a quantum circuit. Okay, so let me go to my iPad. Let me make sure that I have eyes on the chat. Okay, so far no questions, if I'm correct. Yeah, okay, no questions. Okay, still shared. Okay, so this is the idea of QAOA. Why does this work, and what quantum circuit do we use? That is the question. Okay, so let me write down QAOA. The reason why it works is quite simple, actually. So I H bar D over dt psi is 8 psi. I think yesterday Sebastian showed this. Are people familiar with Schrodinger's equation? Is everyone familiar with Schrodinger's equation? If not, I won't use this. Okay, Chris says yes. Anthony says yes. That says yes. Serge says yes. Only 4 people. Okay. So anyway, so this is the Schrodinger equation that solves for basically finding the solution to this state vector given some Hamiltonian H. Okay, so I will not get into this because only 5 people raise hands. Okay, so the idea of okay, what I'll do is I'll just frame QAOA as a variational algorithm, because we don't really need to fully understand in detail why the ansatz make sense. What do I mean by ansatz? So in variational algorithm, I mean, everyone is on the same page with me that variational algorithm works like this. Okay, let me write this as some input X. Okay, and I find the optimal theta, right? Theta star. Okay, so what is happening in QAOA is basically this U of theta is specific, right? So U of theta is UC and UM. And then I do measurement like this. And UC, remember my HC in the case of max cut was something like identity minus GIGJ, right? Where IJ is in the set of edges, edges. So for example, would be 0, 1 is an edge, right? It's written as this tuple in this graph. 0, 1, 2, 3. So this is an edge, for example. This was my cost Hamiltonian. So this is the first step. Okay, let me make sure that you understand how VQEs work. First step is always writing a Hamiltonian in the operator form in terms of these Pauli operators. If you have not heard of Pauli operators, these are basically X, Y, and Z, and identity. You also saw them as gates. X gate is the bit flip operator. Z gate is the phase flip operator. Identity does nothing. Y hasn't been introduced, but it's also another Pauli operator. Okay, so this is the first step. The second step is choose your ansatz. Choose U of theta. What U of theta are we going to use? And this is let's say a hyperparameter, right? So just like in neural network, what is the architecture of my neural network going to be? Is it going to be a deep neural network where all of the nodes are fully connected? Is it going to be something like transformer architecture, right? Or is it going to be LLMs, something like that? You can think of, in a way, okay, so maybe not different architectures, but rather I would say how many nodes in my classical neural network, how many nodes am I going to use and what will be the architecture of this neural network? So like how many, let's say here I use 5 nodes, right? Here I use 4 nodes, here I use 3 nodes, so on and so forth. So this is up to you to design, up to the user to design, right? Or let's say the engineer to design. And similarly here, this is actually quite a hard task because you want a U of theta that is going to capture the solution, right? And how are you going to do this? This is an important question. We will revisit QAOA again, so I won't really tell you why exactly does this work, but this is how QAOA works. Just keep this in the back of your mind. Okay, so U of C is actually just defined as exponential of I gamma, function of gamma, HC. And in this case, if you exponentiate this, the sum will just become product. Why does the sum become product? Because exponentiation of sum, like you learned this in school, I hope. So exponentiation of sums, for example, it's just product of them. And here, these are just numbers. Let's say x1, x2, x3s are just numbers. This is the same case with operators, assuming that they commute. This is actually quite important to remember. So I should also introduce commutativity, which basically tells you that if an operator A and B commute, this is defined as AB minus BA. Okay, so if this is 0, then you can do this product form. If not, then this is actually incorrect, and that would be just an approximation. Okay. So I can give you an example, and you can also verify this. Actually, X and Z do not commute. It's not 0. You can verify this. Write down the matrix of X and Z and see that this is actually not equal to 0. Okay, so if I had like something like exponential of I theta, X plus Z, I wouldn't be able to write it as a product. It would be an approximation I won't get into what this approximation is called, but this wouldn't be exact. Okay, just keep this in mind. And there would be second order terms, third order terms, so on and so forth. But yeah, this is not true. Okay, so in general, this is, let me just call it, this is not exactly equal if they don't commute. Okay, you've taken quantum mechanics before, you'd have encountered this, but if not, I just introduce it now. This is important in designing this type of unitaries, U of theta. Okay, so in this case, we're lucky. Why are we lucky? It's because we won't have to deal with operators that do not commute. If you look at your cost Hamiltonian, this just has terms Z1, Z2, Z2, Z3, so on and so forth. And because an operator always commutes with itself, and an operator would also commute with an operator that acts on a different qubit. So for example, C1 with any other operator acting on second qubit will commute. By the way, this just basically means that because these are acting on different qubits or different systems, the order in which you apply doesn't matter. This is what this is saying. Okay, so for example, let's say I have 2 qubits, right? Like this. I don't care which qubit, which gate I apply first. Like let's say I apply Hadamard here, let's say I apply X here. I don't care if I apply X first or Hadamard first, right? The result is going to be same. And so if the operators are actually acting on different qubits like this, A1, A2, then they will commute, okay? Assuming that this is only acting on the first qubit and this is only acting on the second qubit. Is this clear? Can I get a thumbs up if this idea is clear about commutativity, specifically when operators are acting on different qubits? Thank you. I see a number of thumbs ups. I'd like to see more, but please ask questions, okay? If anything is not clear. Okay. So because Z2 commutes with itself, right? Because an operator is always going to commute with itself, and Z1 and Z3 are acting on different qubits, these two guys will just commute. And I can tell you that all cooperators will commute with each other, which is why I can just separate it down. So I can just write it as a product, okay? Like this. I'm going to ignore the identity term because I'm just going to get a global phase, right? So it's just going to be something like this. So that will be ignored. Sorry, identity. So I just have Gn minus 1, Gn, okay? And so this will be a gate I will apply. This will be the gate, the unitary gate I will apply. Now, how to synthesize this gate is another concern. Because now, okay, so this is great, right? Because I have followed my first step. Using the problem definition, I wrote my Hamiltonian down. I also know how to, for example, write down my unitary, just exponentiate with this parameter if I want to do QOA. But the question is, how do I go from this to a quantum circuit, right? Because like, what is this? Rotation along Z1, Z2, what does that even mean? So because it's, let's just focus on 2 qubit system. Okay, and let's say you wanted to apply this gate, gamma, Z1, Z2, okay? Then I can tell you that this is simply done by doing a C naught. Here I'll do exponent of I gamma Z and then a C naught. And what is this? This is just your rotation by angle gamma. Okay, so exponentiation of some parameter with x, y, or z will just be rotation along that axis by, actually this has to be 1/2. So just make sure that is the case. So this will be 2 gamma. Okay, this is a little bit confusing, but this is the circuit identity. So you can verify this. You can start from your state apply this guy, and then get some state vector, right? And do the same thing here. You'll see that you'll get to the same state. And this is not true just from 0, 0. It's actually true from any state. So to check, actually apply the Hadamard gate, because it's going to take you to the uniform superposition of all states, right? And that means I'm testing it out on all different states. I start with 0. So this will you have to take it as a given, but you are welcome to verify this. Okay, so this is how we went from, but I want you to focus on the high level picture, which is I define my problem formulation in operator form, and then I synthesize some unitary by exponentiating it like this, and then I go to a circuit level, and I can just use circuit identities. So I can also tell you that what if there was like, I don't know, what if there was a nightmare like this, G1, G2, all the way to Gn, right? How do I write this as a gate? So there is a circuit identity. I can just tell you. It actually looks like this. So C naught, C naught, C naught, rotation gate, and then C naught back. This is circuit identities. Okay, so I will not give you a proof for this, but you can just keep it in the back of your mind. All you need to know is synthesizing an exponentiation of some Pauli with some parameter can be done on a quantum circuit level. And once this is prepared, okay, so now we have this U of theta. So I had my initial state psi of x. I have some U of c. I have synthesized U of m for now the other U of m, right? So remember U of m, I defined it. Sorry, first of all, let me call it what HM is. This is just sum of Bit-Clip operators, so x1 plus x2 plus x3, so on and so forth. So UM will just be exponentiation with some parameter, let's say beta, HM, okay? And this basically means I need to exponentiate it like this. Plus. Okay, so can someone tell me what this is? The hint is that all of the terms will commute with each other, right? Because they are acting on separate qubits. So what can I do? See nothing on chat. How can I simplify this? Because remember, I want to get into quantum circuit level. RZ on, remember I have X. I have X1 plus X2 plus X3, XM. So what would this be? Right, as product. Okay, that's the first step. Oh, that's Pascal. Okay. So write this as a product. Yes, exactly. The reason why you can do that is because they commute, right? Okay, very good. But like, how do I implement this on a circuit level? What is this gate? Remember, I told you this, right? I told you exponentiation of I gamma C is just rotation by angle 2 gamma. So what do you think is exponentiation of I beta x? This is my rotation gate. To prove that, you can prove this out, but I'll skip it. Yes, so it's just going to be rotation x gate by angle 2 beta. And so same thing applies for any Pauli operator. Remember, Pauli operators are x. I'll ignore identity, x, y, z. Another rotation, yeah. So yeah, very good. Okay, so now you have learned how to go from Hamiltonian, or at least you have seen an example how to go from Hamiltonian to gate level to synthesize unitary. And once you do that, then you just make the measurement, and then you pass this information to a classical optimizer. Okay, any questions? Because now we'll get to the hands-on. Oh wait, before I get into hands-on, I do have some few remarks slides. But I might skip those because I am running over time already. Any questions about this? About the 3 steps that I described? From a classical problem to a Hamiltonian that maps in a, that represents the problem in operator form, and then applying set of gates that I want to train on, essentially. Okay, so I was supposed to end this lecture at 2:30. And the hands-on is supposed to be at 3:15. So any questions on this? I'm going to assume no, because no one is asking any questions. Okay, very good. So play from current slide. Okay, so I was here before, right? I told you the steps. Yeah, so in this is basically what I said, but it looks nicer in this slide. So you have UC and UMs, and in QAOA, what you do is you repeat this certain times. And actually, as you increase the number of layers, the accuracy actually improves. Not if you get stuck to a local minimum. Okay, so that I should tell you. And the problem with noise is there's something called noise-induced barren plateau, which means noise actually make you get stuck to a local minimum. That's another problem. The problem with using multiple layers by repeating these layers is as you increase, you'll use more gates. More gates you use, the noisier you'll get. Noisier it gets, the likelier you are that you'll get stuck to something called this barren plateau or the local minimum. However, the theory of QAOA tells you that theoretically, as long as you apply infinitely many number of layers, you will actually get to the global minimum, or that mean approximation ratio that I defined earlier becomes 1. Okay, so this is the trade-off that we also need to keep in the back of our mind. Problem formulation is one thing, but if your circuit depth is very high, then your variational algorithm will be futile, right? That's something to keep in mind. All right, so how to interpret the result? So this is an example of using Maxcar with 1 layer and 2 layers. Here, 2 different like gradient estimation techniques were used. And you see that with 1 layer, it gives you the state output 0, 1, 0, 1 and 1, 0, 1, 0. 0, 1, 0, 1 basically means, remember I encoded 0 to refer to blue color and 1 to refer to red color. So this is basically saying color the diagonal vertices, right? Or the vertices. So basically it's saying that, let me go back to my answer or the optimal solution here. So here I had diagonally opposite vertices of same color, right? So for example, 0 and 2 were of same color, 1 and 3 were of same color, and the same case here, right? So that is actually represented in our solution, right? You can see that 0, 1, 0, 1 means I need to color the opposite vertices with the same color. And the same thing is encoded here. So this is saying first vertex would be red, blue, red, blue. That is the correct answer. But you see that, so this is run on an ideal simulator, which means it doesn't involve noise. If you run 2 layers, you see that these 2 states only survive and the rest actually vanish, these small peaks. So it is true that as you increase the number of layers, QAOA will give you a solution that is very close to the optimal. Okay. Now, how does this compare to classical technique? It's very important discussion to have. Because I already showed this slide, Fari et al. Showed in their paper that for D-regular graphs, you get with 1 layer, you can get 69% mean approximation ratio with just 1 layer. But with the classical algorithm, we already have something called semi-definite programming. You can get up to 93% approximation ratio, right? So with 1 layer, classical algorithm already shines. And this is for specific graphs. It's called D-regular graphs. I won't get into that. And classical semi-definite programming also tells you that for generic graphs or arbitrary graphs, you can get at least 87% mean approximation ratio. With current QAOA, especially by running them on noisy device, we get nowhere above 70%. If you look at like a bunch of experiments people have run. Okay, so we're actually far off from the best classical optimization algorithm, even for small sizes. And this is where, you know, the state of the variational algorithm is in. And this table actually summarizes it quite well. But this is just to inform you of the current state. But yeah, as you increase, you know, p to infinity, r gets to 1. This is the theory of QoA. And we have a person, a researcher, scientist. Some of us consider him as a guru. Scott Aronson. He writes like very interesting blogs. And he's very critical about, you know, he's constructively critical about quantum computing. So this is a nice quote. QAOA, a quantum algorithm that incredibly, for all the hundreds of papers written about it, has not been convincingly argued to yield any speed up for any problem whatsoever. Besides, as it were, the problem of reproducing its own patterns of errors. And this is a criticism of QAOA. You can't really take this as criticism of the whole variational algorithms. But yeah, I mean, there have been so many papers published on QAOA trying to, you know, claim speed ups. Not really. Yeah.